Hi guys, let's go ahead and get the pen going and let's change the color to something that we can sell. Let's stay with red. So in this sound assignment C, we're looking at a spring constant, at springs, how they vibrate. Now, to let you know how this works, get my pen back, there we go. So when we look, so we have a spring. So if I press the spring down a certain distance and now relax, it's going to go up and down. Sorry folks, it's me holding my pen. This is the equilibrium point, and it's going to vibrate for about a couple seconds like this until friction slows it down and it comes to a stop. So when we look at springs vibrate, this is what we're looking at. The period that it vibrates is not related to length, but the mass. So m is mass, and that's the mass of the object on the spring. And we know that K is the spring constant. Two pi is normal, so T is the period. And the period of time it takes to go from here up and back. So like a pendulum, we're looking at, if we start here, the period is the time it takes to go from point A to point B, back to point A, going the same direction, going back up. So this is what we call the period. F is the frequency, how many times it does that per second. So the period must be in seconds, frequency must be in 1/, seconds or hertz, and mass is going to be in kilograms. And I hope this all makes sense. So let's look at the first problem. Well, we're talking about something interesting. We're talking about male mosquitoes and how they hear. They have very selective hearing because females emit a frequency of about 230 hertz, which the males can hear. Nobody else can. So what we're going to do is say if we want to research this, we have a spring. And it has this spring constant, 1.14 times 10 to the fourth. Now we want to know what mass we need to put on this, so when we vibrate it, it has the same vibration frequency as this mosquito. So frequency is 230 hertz. Come back up here, and we need shrink K is 1.14 times 10 to the fourth. So we're going to take time is 1/230, which is the frequency. And we're going to figure out the period that it takes for one oscillation. So that's going to be, and I'm going to take this out a couple of digits because I'm going to use this calculation a little bit later, and it's going to be a very small number. So it does this fairly quickly, 4.3478 times 10 to the minus 3. So this period is equal to 2 pi times the square root of the mass over the constant. And we want mass. We want to look for the mass of this. So what we're going to do is go from the inside out, or right to left, to figure out how to solve this. So and I'm not going to put the numbers in right now, but I'm going to use algebra to get mass isolated. So first thing we do is square both sides. T squared is equal to 4 pi squared times mass over K, our spring constant. So rearrange this, multiply both sides by K. So T squared times K is equal to 4 pi squared times the mass. Divide both sides by 4 pi. T squared times K over 4 pi squared is equal to the mass. Now put the numbers in. 1.114 times 10 to the fourth. That's K times T, 4.3478 times 10 to the minus 3, and we're going to square that number. And we're going to when we get that answer, we're going to divide by 4 pi squared. That's going to give me my mass. And the mass is going to be in kilograms. So I would take that 4.3478 raised to the minus 3. Let's square that number first. And then take that answer and multiply it by 1.14 raised to the 4th. So you get like 0.215, and then we're going to divide that by 4 times pi, which is then squared, and the number I'm going to get, the mass. The mass is equal, whoops, sorry guys. The mass is equal then to 5.45 times 10 to the minus 3rd kilograms. And that's the answer that's the answer we want. 5.45 times 10 to the minus 3 kilograms. And this is how we answer that. All right, so you're going to get various problems with this, and if you look at this equation, we're going to find mass with time. Sometimes we may find K, but doing the same type of algebra, folks.